and welcome to this tutorial on guessing a distribution. This tutorial is going to be divided into 3 videos. The first video, the current one you are watching, would focus on giving you an introduction to the chi-squared goodness of fit test. The second and third video would be demonstrating this test in a tool which is Python for us. So what is the chi-squared goodness of fit test? This test is basically going to be used to see if the proposed distribution or the hypothesized distribution for the population is a good fit for the population or not. So that is going to be the focus of this particular test. And what is required for performing this test? We require something known as the frequency table. So the frequency table is going to consist of 3 columns. The first one is going to be the bins, right? So these are going to be the ranges over which we are going to be capturing the values. So those are the bins. So let's say we have bins 1 up to k. So we have k different bins, and for each of these bins we need something known as the observed frequency. Observed frequency, let's call this O1 up to OK. So these are the values that we observe in a sample that is got from the population. So how many observations in the sample fall in bin 1? How many observations in the sample fall in bin 2? How many observations in the sample fall in bin k? So that is going to be the observed frequency. The third column is going to be the expected frequency. If this sample is indeed coming from a population, then what is the expected number of outcomes E1 that is going to fall in bin 1? Similarly, how many observations should fall in bin 2 if this sample is really coming from the theorized population distribution? So that is E2, and so on up to Ek. So this is going to be the frequency table which is going to be used for performing the chi-squared goodness of fit test. And thus far, in your statistics course, this table would have been given to you and you would perform the test. So how would you perform the test? You will compute the test statistic, which is going to be the chi-squared statistic, and this chi-squared statistic is going to be computed as O1 minus E1 the whole squared by E1, O2 minus E2 the whole squared by E2, so on and so forth up to OK minus EK the whole squared by EK, right? So the summation of these values, summation I is equal to 1 to k, OI minus EI the whole squared by EI, this is going to be the test statistic that you are going to compute given this frequency table. Now, once you have got a test statistic, how do you conclude whether you are going to accept the null hypothesis or reject the null hypothesis? That is going to be the end goal of any test, correct? So for that, you can use 2 approaches. The first approach is the p-value, right? So for this chi-squared value that you have got, you will compute the p-value. I will not go into the computations since that is in your basic course, but you will compute the p-value, and if the p-value is lesser than your significance level, which is your alpha, you would conclude by saying reject H0. So that is going to be your conclusion. If your p-value is lesser than the significance level alpha that you are setting, then you will reject the null hypothesis. On the second technique, this is, let's say, method 1. In method 2, you will for this computed test statistics, you will calculate a chi-squared tabulated value let's call this tabulated value at a degrees of freedom, which is given as k minus p minus 1. I will come to the b in a minute, at a level of significance which is alpha. And your conclusion would be reject the null hypothesis if your chi-squared tabulated is lesser than your chi-squared computed, right? So, if your chi-squared tabulated is lesser than this computed test statistic, then you will reject the null hypothesis. So, that is going to be the final conclusion. Now, what is this p? This p is the number of parameters in the population distribution that you need to compute for a given test, right? So, this p would vary from based on the distribution that you are assuming. So, let us say we are going to be looking at two distributions in our demonstration. So, I will give you the values for those two. Let us say you are telling the population follows a, let us say, a uniform distribution. For a uniform distribution, the two parameters that you will be computing are the lower value and the upper value, which is a and b. So, in this case, for a uniform distribution, the p is equal to 2. Whereas the second one, which is the Poisson distribution, for a Poisson distribution, the only parameter that you need is lambda, right? So, everything else is got based on that lambda. So, in that case, p is going to be equal to 1, which is your lambda. In the uniform distribution, it is going to be a and b, the lower value and the upper value. So, these number of parameters that you are going to compute will vary from distribution to distribution. Let us say we take a third one, which we are not going to demonstrate, but which is very common, which is the normal. So, for a normal distribution, you need the mu and the sigma values, or the sigma squared variance, the sigma or the sigma squared, right? So, in this case, the p is going to be equal to 2. So, for every distribution that you are going to fit, you must know the number of parameters that you need to compute for the distribution, and since you are going to compute them using the sample, so many degrees of freedom will be reduced from your chi-squared test. So, your chi-squared test k minus p minus 1 would be k minus 2 minus 1 in the k when you are doing it for a Poisson. It will be k minus 1 minus 1 when you are doing it for a Poisson distribution. It will be k minus 2 minus 1, pardon me, for a uniform distribution. It will be k minus 1 minus 1 for a Poisson distribution, and k minus 2 minus 1 again for your normal distribution, and k is going to be the number of bins that you use, right? So, k is the number of bins, p is the number of parameters that you are going to compute using the sample for the population, and minus 1 is an additional degree of freedom that you will be losing. So, this is the degrees of freedom DOF. So, when you look at getting the tabulated value, so chi-squared tabulated is obtained for a degrees of freedom and at a given significance level alpha. And if this tabulated value is lesser than your chi-squared computed value, you would reject the nulls. If not, you will not reject the null hypothesis. So, this is the initial introduction to the chi-squared test that you have studied so far in your statistics course. Now comes the business perspective. Till this point is pure statistics, right? And however, for all of this test to work, you need this particular frequency table to be available for you. However, in the actual business world, you will not be having this frequency table. You will only be having a data set, and the data set usually would look like, let us say, the observed value. Let us say we are talking about the first distribution that we will be talking about is uniform, right? So, in our tutorial, so for that, let us say we are measuring the length of a scratch. On a vehicle that is manufactured. So you are going to manufacture a vehicle, and during the manufacture process, let's say scratches happen, and you are going to measure the length of the scratch. So the length of the scratch is going to be, let's say, in mm. So what do you have? You have an observed value which is going to be like 1.1, 1.5, 0.5, 0.7, 0.9, 3.0, whatever, right? So these are going to be the values that you actually get, and these values you must then convert them to a frequency table and then say whether these are following a uniform distribution or not. So the objective of this entire tutorial is to show you how you, given a data set like the observed values with their let's say length of scratch in mm or number of defects, let's say, so on and so forth, given that data set, given a list of observed values, how do you convert it into a frequency table? And once you have converted it into a frequency table, how do you identify, how do you perform the chi-squared goodness of fit test, and whether accept or reject, do not, whether you reject the null or do not reject the null. So that is going to be the entire discussion in the remaining two videos of this particular tutorial. We would stop here, and in the next tutorial we would pick up fitting a distribution for a given data set which is going to be uniform, which is coming from a uniform population.